Now we're getting into our second invited talk of the session. And I'm delighted to present Vivek Boominathan, a postdoctoral researcher from Rice University, where he also did his PhD with Ashok Veeraraghavan. Vivek has made numerous contributions to lensless imaging over the past almost 5 years or more. And today I'm tell us what the recent advances are in the area. Vivek, take it away.
Thank you, Achita. Thank you for the introduction. Welcome, everyone. Thank you for being here for the talk. I'm Vivek Boominathan, a postdoctoral researcher at Rice University. And today I'm going to talk about recent advances in lensless imaging. Let's start with the conventional optics that's used in your cameras and every camera in general. That is lenses. The one element we are going to try to replace in this talk. So conventional optics, which is lenses, try to focus one point in the scene to a point in the sensor. In essence, the goal of lens design is to directly capture a perfect image of the focus plane and without any need of additional processing. However, there are limits and trade-offs when it comes to lenses. A simple one we can imagine is it directly maps a 3D scene onto a 2D image, losing three-dimensional information. And there are other trade-offs like trade-off between resolution and field of view, trade-off between light throughput and depth of field. Lenses can get heavy. And also there is a constraint on the thickness of the camera due to lenses, which we will touch upon later. Now, we have tried to solve many problems of the lenses using computational approach. Here is one example of modifying the lensing optics and adding computation so that we can reconstruct the depth image directly from a single capture. However, all of these approaches don't really get rid of the lens, but use the lens and capture an image that is still perceivable by humans. That means I can look at this image and say there's a leaf. And then with some processing, we are able to extract information. But none of these optics have gone beyond thinking beyond how lenses can work. In the sense, do we have to maintain this focus to capture an image directly to do many use cases? And that's where we are going to talk about how the lensless is going to help. Now, one particular advantage I'm going to pivot on, at least to begin with, to motivate lensless is basically talking about the thickness and size of the camera. Now, for conventional cameras with the lens needs to be at a focusing distance away from the sensor. If it is not at the distance, it's going to produce blurry image. Now, this we can say is kind of a constraint placed by the lens. And what we want to do is we want to explore ways so that we can make this camera way thinner and be beyond the constraint placed by lenses. Now, just briefly, why do we want thinner and miniaturized cameras? There's actually a ton of reasons for that. There are reasons where you want to put it on micro drones for surveillance and rescue. There are many places where you want to put it on wearables so that you can have continuous bioinformation about your body. And also there are other places where you can put such miniaturized cameras such as endoscope, observing the neural activity of brain as an implantable and even as an ingestible camera. So with all these applications, one of the driving forces is we need to miniaturize these cameras so that we can make it usable for all these applications. Now, lenses, the design of lensless have acknowledged this necessity, which is miniaturization. And over the years, with different technologies, we are able to reduce the size of the camera using, in the beginning, digital sensors, compound optics, and now plastic optics. But still, with few millimeters, 5 to 7 millimeters of your smartphone camera, making it thinner is going to affect how the imaging capability is going to be. So in that case, what we are going to introduce is to go beyond such lensing optics, which tries to focus light. What we want to do is we want to replace the lens with a thin optical mask that's not going to do focusing, but rather it's going to map a point in the scene to a 2D pattern, a larger pattern. Instead of a point to a point, it's going to be a point to a larger pattern. What we call this pattern is like a point spread function because it's a response to a point. And in this way, we don't need to continue having this focusing distance as our thickness constraint. We can go smaller than the focusing distance and achieve smaller thickness of cameras. But doing so means we need additional requirements. Case in point, when we see the sensor measurement, it's not like an image that we can process. We cannot look at this measurements and say, oh, I see a Santa Claus there. Instead, we need an additional computational algorithm to go back to the image. So in essence, a lensless camera is a fully computational camera. That is, it reduces the thickness by replacing the lens, and it relies on computation to do the focusing, or basically to recover back the image. Now, with such a camera, it doesn't mean that we lose information. We actually retain information, and we are able to reconstruct video, able to do face detection over the reconstructed image. Basically, we are still able to capture all the information that is important in an image, but achieve it using thinner cameras. So just to combine it with the advances over the years, computational cameras are allowing us to go way thinner in camera and use computation to reconstruct images. Now, I just want to take a slight detour so that I acknowledge the work done before the type of cameras I'm going to talk about. So between 2007 and 2015, there was a different kind of lensless imaging that was trending. That is an illumination encoded lensless, in which case the illumination is behind the scene. And the way the encoding is done is how the objects interact with the illumination. In the talk I'm going to give today, I'm going to show the recent advances in lensless imaging, which is mask encoded lensless imaging, where it doesn't place any constraint on where the illumination is. We expect ambient illumination, and then the scene reflects the ambient illumination, just like in a normal camera sense. And that's what we capture and reconstruct. Now, in this lensless imaging setup of a mask encoded lensless imaging, we can break down the anatomy into two parts. One is the camera itself, the optics, the sensor, the design of the distances. So that is one part of the lensless imaging. And the other part of the lensless imaging is the computational algorithm that we are going to use to recover back the reconstruction. Now, when we come to the camera, so there is a couple of anatomy within it, which is there is the mask that's going to encode the incoming light. There's a sensor that's going to capture the intensity image. And then the design parameters are the thickness, which is the distance between the mask and the sensor. And the other thing is what is the response of the mask, what we call the point spread function. So over the next few slides, we are going to go over the lensless anatomy. But briefly, I'm going to mention the computational algorithms used. There are different versions of algorithms that have been used. There can be a single step solution, usually very fast, but can have lesser quality. Then there is iterative convex optimization, which produces really good images, but takes a long time to run. And finally, there is, of course, the machine learning data-driven approach of feed-forward neural network, which is both fast and is able to produce really high quality reconstruction. So over the next few minutes, I'm going to focus on the anatomy of the lensless camera, which is the mask and the sensor. Now, many masks have been explored over the years, over various works. There is amplitude mask, which is basically this incoming light, and it's going to modulate by allowing and blocking light at different points. Then there is the, and in case of amplitude mask, allowing and blocking light, that can cause either shadows or using, it can also be modeled using diffraction to produce specific patterns. Here is an example from a paper that used Fresnel zone apertures. Another type of mask is phase grating. Definitely going from amplitude mask onwards, amplitude mask is going to block light, which means there's going to be less light throughput. The next three types of masks are going to allow all the light to go through, and so having better light efficiency. In case of phase gratings, the phase delay or the retardation of light is only either 0 or pi. So phase modulation is either 0 or pi. Then there is diffuser, which has a statistical distribution of phase retardation and can produce phase delays from 0 to 2 pi with a rapid. And finally, there is a phase mask, direct designing phase mask, which produces phase modulation at discrete phase steps. So you can choose what is the step size you want based on fabrication, and then you can do phase modulation of light at those steps from 0 to 2 pi discretized. And below, I'm basically showing an example of amplitude mask, an example of phase gratings, an example height profile of diffuser cam, and an example phase mask being used. So just to compare, amplitude mask being easy to fabricate actually blocks light, but it does have its advantages over beyond visible, which we'll touch upon briefly. And the other three types of mask are completely light efficient. It allows all the light to go through and is able to produce images. Now, as a case study, let's look at a specific example of lensless camera, which was developed by us and published in 2020. We call FlatCam, which is a phase mask designed lensless camera. In this case, the mask is a phase mask. It modulates the phase of the incoming light. The sensor is a normal CMOS sensor. The thickness is less than 2 millimeter, coming at the thickness constraint, able to do much less than 5 to 7 millimeter thicknesses, which are in your smartphone. And in this case, we can look at how the fabricated phase mask looks like. It's basically, we can think of at different heights on glass, allowing for different phase retardation of light. Here's the phase mask profile, and here is the point spread function that we capture using the phase mask. And this is designed such that it produces as higher quality a reconstruction. Now, in the next few slides, we are going to use convex optimization based computational algorithm. In this case, it's a single step reconstruction. We can see that the captures are muddled or multiplexed, which we can't interpret. By reconstruction, we are able to reconstruct. This particular lensless camera also has a three-dimensional response to the scene, which is if it's close enough, the point spread function of the camera actually changes in size or magnification. And we can plot the correlation of all these point spread function over depths. And we can see a particular trend which we can exploit. In this case, when we look at the correlation between point spread functions at medium level depth, we can see that the correlation basically have a broader width, which means we can't directly detect depth probably, but we can actually do refocusing. So here is an example of refocusing at 3 different depths. We capture a single image, but then computationally refocus at the front, the middle, and the back. So this is refocusing. If we get even closer, we can see that the point spread function over depth, its correlation decays really fast, which means now we can exploit that to reconstruct 3-dimensional information. So in this case, we take a single capture of the scene. The scene is a text light at a slanted, written on a slanted plane. And then using an iterative convex optimization, we are able to reconstruct the image, the 3D information. So let's quickly talk about the theoretical resolution characterization of any lensless camera. It can actually be intuitively said that a resolvable feature is having a width such that its translation of point spread function on the sensor is 1 pixel pitch. Now, this is a theoretical resolution, and we always try to reach the theoretical resolution. So in that sense, a resolvable feature can be calculated in a theoretical sense as sensor to mask distance divided by the scene distance times pixel pitch. And using FlatCam, we are able to match this theoretical resolution, and we have done a USAF target characterization. The other thing about lensless camera is like the field of view. the field of view of a lensless camera is actually very large, and it's limited by the angular response of the pixels. That is, what is the pixels response over different angles, and this theoretically should be the field of view of the sensor. However, in practice, our best reconstruction is in the center, and as we go towards the edge of the field of view due to degradation in the point spread function, as shown by this plot from Refocusing, that the quality of reconstruction starts to degrade in the slightly outside field of view. But one thing to take away from this is every pixel actually encodes every point in the scene. That is, every sensor pixel is seeing almost the entire scene. And this was actually exploited for doing a single image to video reconstruction. This work from Berkeley, they basically capture a single capture from rolling shutter and are able to reconstruct the entire video based on a single capture. The same idea was exploited also for spectral imaging. Again, the spectral sensor, since each pixel sees the entire scene, we can use computational methods to reconstruct multispectral images or hyperspectral images from a single measurement. Keeping on the same note as spectral, lensless allows you to go beyond visible light imaging without having expensive optics. In this work, they showed long wave infrared imaging or thermal imaging using an amplitude type mask. So showing this gives the advantage of lensless to also be used beyond visible light without a huge increase in cost of the optics. Okay, so we talked about the lensless camera side. Now let's talk about computational algorithm side, specifically the feed-forward neural network algorithms. So these algorithms are neural network or convolutional neural network based systems, which is able to take a measurement and produce really high quality reconstructions. And most of the works related to this can be broken down into two parts. One part which uses the camera model and maps this highly multiplexed blurry image to an intermediate result. And the second part takes this intermediate result and enhances it to produce higher quality perceptual images. And the training data can be experimentally captured by using monitor display with the camera. So you get measurement and the ground truth. Here are two works which have different ways to implement the camera model into the network. In FlatNet, in the top case, we incorporate the camera model, either it's separable model or non-separable or convolutional model directly, but we learn the parameters of that model. The other alternate approach that was explored was not learning the camera parameters, but using unrolled layers of iterative algorithms and optimizing the parameters of the unrolled layers. And these are two ways to incorporate the camera model, which produces an intermediate and is able to then use a perceptual enhancement network to reconstruct a higher quality images. Here is an example of showing reconstruction quality. If we simply do simple least squares reconstruction, we get the middle, but then using the feed-forward network, we are able to get highly perceptual quality images. Here is another comparison. As we can see, the measurements are pretty blurry. With single-step Tikhonov solutions are pretty noisy and can lose the details. But using the two data-driven approaches, we are able to have high-fidelity reconstruction images. So that's with the data-driven approach. Let's quickly go through emerging applications and future applications of lensless imaging. One of the things lensless imaging is going to have big benefits is in microscopy. In this particular case, in flat scope, we showed almost 4 times the bigger field of view while maintaining the same resolution. Another case is we have shown in vivo imaging of brain neuron imaging. Here is the brain video with different neurons and the blood vessels seen. And here's work by Berkeley where they imaged the larval zebrafish expressing GCAM. So there is a lot of emerging applications in microscopy, and that's continuing. Future applications, there's upcoming devices that can do modulation at high speed. Now, can we incorporate that for lensless imaging? So on the left case, this algorithm was designed as a depth-aware system so that we can directly do refocusing. In the other case, they explored reconfigurable nanoparticles that change patterns based on electric field to do programmable reconstruction. And one other future application, which is a hard problem today, is designing it for privacy. We know that the measurements are blurry, but then can be exploited for privacy. But there are challenges in which we need to add loss of information or bottlenecks so that we can achieve privacy. And this is an ongoing future direction. To conclude, a ton of impact. Yeah.
Little over time, so.
Yeah, I'm almost done. This is the last slide. So there's a ton of impact, and I hope I motivated you regarding the lensless imaging, and thank you for listening.
Okay, thank you very much, Vivek. I think we extended a little bit of the allotted time, so we won't really have time for QA, but maybe I'll just ask one lightning quick question here. A really exciting culmination of your work, Vivek. Great to see. I can even see from the images you captured that your own hairstyle has changed over the years. You know, where do you think, what do you think is the next big milestone in lensless? Is it going to be commercialization to industry, or do you think the next milestone will come from continuing the academic research? Obviously, it's a balance of both, but what are you most personally excited about if you had to pick one?
So I think there is good amount of work that shows promise for commercialization. There are challenges, of course, but I think those challenges are getting solved as we go. So I think one of the next exciting things is to introduce this into commercial applications where you can have in-display cameras and many other places where this can directly get integrated to commercial products.
Thank you very much. And I highly encourage you to visit Vivek's website and get to know him better. Thank you, Vivek.
Thank you.